Hello, this is Huayi Li. I'm a PhD student at the University of Michigan, Ann Arbor. I'm co-advised by Professor Ilya Komnovsky and Professor Anouk Gerard. The title of our presentation today is A Failure Mode Reconfiguration Strategy Based on Constrained Admissible and Recoverable Sets. Our study focused on the design of failure mode and effect management system for industrial applications. There's great demand for systematic design approaches in this area, as the software and algorithmic content for diagnostics and FMEM system is often larger than what is responsible for the nominal system function. This is notably the case in the area of advanced and autonomous vehicles, where redundant actuation is often employed to enable safe operation in case of failures. Examples include having dual steering motors and the use of redundant brake actuators as shown by these videos. So our goal to the design of the FMEM system is that in case of a single point of failure, the system operation can be reconfigured so that in a new mode, another single point of failure cannot lead to safety hazards, and at the same time, we're maximizing the system availability. Systematic recoverability analysis have been addressed in previous literatures, but the existing methods typically do not handle state and control constraints. Set theoretic control methods have been used to handle constraints, so our approach builds on the idea of using constrained admissible and recoverable sets while extending it to cases with multiple failure modes and sequential mode transitions. We consider failures caused by actuator being zeroed out, and the goal is to guarantee safe operation in reconfiguration of the system, which means to avoid the violation of state and control constraint at all times. Last but not least, our approach includes the important feature of reference checking while maintaining the safe operation of the system by using the reference governor. Here's an outline for the rest of the presentation. I'll first introduce the dynamic and constraint of the type of system that we're considering. And then we will formally define the constraint admissible and recoverable sets, which are then used to develop the safe operation and reconfiguration strategy. And finally, we will see two numerical examples using the proposed method. We consider systems with the open loop dynamics shown by equation 1 and 2, where M stands for the number of the mode, including normal modes and failure modes. A stabilizing controller is given in the form of equation 3, where Km and Gm are the feedback and feedforward gain matrices, and a closed loop system dynamics can be represented by equation 4. The set of point-wise in time state constraints are given in equation 5 as a finite set of inequalities, which represent state and control constraints, as well as actuator range and rate limits. Modifications to these constraints are considered to facilitate the subsequent design of our failure mode reconfiguration approach. Firstly, to satisfy subsequent conditions for failure mode reconfiguration, it might be necessary to artificially tighten the constraints as given by equation 6, where the set X and bar need to be appropriately designed. Secondly, for some of the state constraints are imposed conservatively in normal conditions to extend the system operating life. They may be able to relax temporarily during the reconfiguration. So as shown by equation 7, where XRM should also be properly designed. For the problem statement, we need a systematic way to design an FMEM system where a failure corresponds to the loss of an actuator and a mode transition. And sequential failures and mode transitions are possible. The system should guarantee that despite failures, it can safely reconfigure upon failure detection and safely operate in each mode while performing reference checking. It is assumed that only one failure can happen at a time, and there's instantaneous detection and isolation of the failure, as well as large time between subsequent failures. And the number of the working actuators should be greater than the number of the references. Here's the framework of the safe operation and reconfiguration strategy. During safe operation, the system runs the upper part of the loop and perform reference checking using the reference governor. Once the failure is detected and isolated, if reconfiguration is necessary, the recovery sequence generator will generate a command sequence and the system will run with the sequence until the reconfiguration is finished. Before further discussion of the strategy, we first need to define the constraint admissible and recoverable set. The constraint admissible set is a set of constant reference command V and the initial state x0 such that the constraints are satisfied for all future time. The constraint admissible set defined by equation A has two nice property, is finally determined as given by equation 9, and it's an invariant set. The recoverable set is a set of initial state x0 such that there exists a recoverable sequence from V0 to Vnm-1 to steer the state into the projection of O infinity m within a certain number of steps Nm, while satisfying safety constraints during the reconfiguration. Now back to the safe operation and reconfiguration strategy. During the operation in each mode, the reference governor is applied. So the reference command is given by RK, while the modified command VK is updated at every time step by solving the optimization problem given by equation 11. When a failure is detected and isolated, if reconfiguration is necessary, the recovery sequence generator will generate a command sequence by solving a quadratic programming problem. The safe reconfiguration condition is given by equation 12, where we need that the projection of the constraint admissible set of mode M to be a subset of the recoverable set of its successor mode M prime. Three mechanisms can be used to satisfy this condition. We could tighten the constraints of the preceding mode, relax constraint of the successor mode during the reconfiguration, and allow more steps for the reconfiguration. An additional mechanism to ensure reconfigurability in the design of our FMEM system is to impose artificial range and rate limits on VK. The limits can be represented by equation 13 and 14. We define ZK equal to XK minus gamma M VK, and we can derive the dynamics about ZK in equation 15. ZFM and SM are shown in equation 16. Then we have the property that ZK will converge to a point in FM as the time goes to infinity, which implies that the system trajectory XK will converge to a point in SM as the time goes to infinity. So as a result, our safe reconfiguration condition can be weakened to equation 17, where we only need the the intersection of SM and the projection of O infinity M to be a subset of the recoverable set of its successor mode. Now let's see two applications with numerical results. The first example is for a mass spring damper system with two redundant forces acting on the mass, and it's trying to check some given displacement. The dynamics, constraint, and definition of modes are shown on the left. And the design process begins from mode 3, where both actuator has failed, and end with mode 0, and that's the mode for the normal operation. We consider two study cases. The first case is without command range and rate limiting, where we need to apply the mechanism of tighten the constraint in mode 1 and 2. And the second case is with command range and rate limiting. We can see that in either case, Reconfigurations are successful when failure happens. The constraints are satisfied throughout the simulation, and in case 2, the effect of command rate limiting is visible. The second example is for the Boeing 747 longitudinal flight control. Again, the dynamics, constraints, and definition of modes are shown on the left. The design is similar to case 1 in the mass spring damper example, except notice that if we only change the step to allow for recovery, the change to the recoverable set is very limited. In order to satisfy the safe reconfiguration condition, we can tighten the constraints of the preceding mode and relax the constraints of the successor mode during the recovery. The simulation result shows that there is no constraint violation during the operation and reconfiguration. To conclude this presentation, we propose a systematic approach to the failure mode and effect management system design based on constraint admissible in recoverable set to handle system with multiple modes and sequential actuator failures, as well as state and control constraint and the need for reference checking. Future work include developing comprehensive numerical procedures and studying for cases when failure detection is either incomplete or unavailable. We hope this presentation can give you a taste of the flavor for the ingredients of our set theoretic approach. For more details of the strategy, please refer to our paper. Thank you very much, and I'll be happy to take some questions.